first one, you could use, remember I told you that if your input is linear, you don't have to do a u sub, you could just divide by the slope. So for the first one, this would just be 3/5 sine 5x plus c. So you just do the antiderivative, divide by the slope of the argument, and you're done. So, looks like everybody got it. I don't think anyone cheated. You all just did a full u sub. So, oh wait, nope, you guys use a shortcut. Did you guys use the shortcut? Or did you just put your u sub somewhere else?
I think we just mentally did that. Yeah.
Oh, no, yours is wrong. You didn't divide by the 5.
Yeah.
You guys just did it wrong. Okay, that's all right. Okay, so yeah, you either have to do u sub or you have to divide by that slope, but somehow you got to take into account that it's a 5x and not just an x. All right. Same thing with you guys. You guys did your u sub.
Yeah, I just forgot to bring the 5.
Yeah, when you rewrote in terms of u, you didn't take into account that 1/5. Okay. All right. Okay, so for the next one, you have a u of ln of 2x. So your du, well, remember the guts go on the bottom, the derivative goes on top. So it just ends up being 1/x dx. So your integral can be rewritten as just u du. So 1/2 u squared plus c. So you get 1/2 ln squared 2x plus c. Yeah, you had it almost right. You're just missing the 1/2. Yeah. Hey, Charles. All right. Yeah. That's right.
So
Yes. Yes. Yeah. When you're writing, it's kind of like sine squared. Yeah. Same kind of thing. Yeah. Alan.
So I have a question about u sub. So all it really is like you undoing chain rule, right?
Kind of. Yeah. It is like a reversal chain rule.
Like for example, like with 3, if you could like reverse the chain rule like in your head, can you just write it like?
Yeah. Yeah.
Okay.
No one
Would that
no
make
one will
sense?
ever require to see a
Okay.
u sub if you can do it in your head.
Yeah.
Yeah. That's sometimes a lot though to do in your head.
Yeah, but some of them are simple. Like 3, like you could probably figure it out.
Some, yeah, I do know people who can do 3 in their heads. I cannot, but there are people who can. So my brain just gets too tired. But yeah, if you can, I'm not, like, I don't require, if you can do it, I don't require a u sub. Okay, especially like now that we're past the chapter where you've learned it. All right, so for this one, pi x squared. So your du is 2 pi x dx. So you have the integral of 1/2 pi e to the u du, which is 1/2 pi e to the u plus c, which is 1/2 pi e to the pi x squared plus c. So, good. Good. Yes. Yep. Yep. Ooh, we rocked on this one. Well done. Oh, whoops. You guys just have a half and not 1/2 pi.
That was an extra way.
Oh, that was an extra? Okay, that's not the final answer. That one's
The
right.
correct way was it.
Okay. All right. Good, good, good. All right. By the way, I want to show you something just for fun. Bless you. So, for this problem, I'm going to do it a little different. I know we're kind of crunched for time, but I still want to show you something. Suppose we let u be the whole e to the pi x squared, and then your du would be, well, it's e to the pi x squared times the derivative of pi x squared, which is 2 pi x dx, right? So then, if we divide by the 2 pi, we have x e to the pi x squared dx. So 1/2 pi du equals the entire integrand. And you could replace the integrand with just the du part. You don't have to have a u in your integrand. if the entire integrand can be replaced with the du, because then it's just 1 over 2 pi u, right? Which is 1 over 2 pi e to the pi x squared plus c. Right? So, kind of fun. All right. And then the last one, which was missing its integral symbol, I'm hoping you guys recognize, you can just write the answer. This is just 3 arctan t. Which most of you got. So well done. Good at remembering your inverse trade. Good. Okay. So today's lesson was supposed to be Monday's lesson, and Monday's lesson was supposed to be today's, but we decided last minute to switch them. So there is one slide where it references something that you were supposed to have learned, but you haven't, and that's okay. Yes? At the end. Yes. So this class ends at 11:12. So at 11, I will stop, and we will give tests back and talk about retakes. Miss Grunwald had a conference that she had to be at from early yesterday morning all the way through. Like, she never got a moment to do anything else, right? And so she got home last night and still had all 60 of her tests sitting there to grade, but she graded them all just for you so that you could get yours back today. Okay. All right. So 6-2A, I can find volume using disks and washers. Washer. What do you say? Washer. Yeah. Disks and washers. So every time I say disc washer, it makes me think of dishwasher, which makes me think there's a scene, if you ever see, there's a movie that's really good. It's about the life of Bruce Lee. It's called Dragon. Anyone seen Dragon, the Bruce Lee story? Okay, do you know what I'm talking about? So he's working as a dishwasher, and his boss, he's getting into trouble, and so she gives him a whole bunch of money, and she says, now you could go out and get an education, or you could just blow it all on, dumb stuff. And she goes, I hope you blow it, because I can always use a good dishwasher. Right? I loved that scene, dishwasher. So anyway, okay, that's nothing to do with poetry. All right, moving on. Here we go. So the volumes that we're going to be finding over the next day, today, over the next hour, are volumes. They're called volumes of revolution. And the reason they're called volumes of revolution is because they can be generated by, if you take the solid, if you stuck an axis through the center and graphed this function just like the side of it and spun it around the axis, would you get the figure, right? So any figure, yeah, exactly, like Jacob's holding up another one, right? So this would be another one if it didn't have the little thingy on the side, right? So you stick an axis through the center, you outline one side, you revolve that about the axis, and you get the whole solid, right? That's called a solid of revolution. So anything that can be created by revolving something about an axis is a solid of revolution, and that's what we're going to be finding volumes of today, right? Really, the technical definition for a solid of revolution is anything where the cross sections are circles. Because whenever you revolve something, you spin it around an axis, your cross sections are going to be circles, right? Okay. So anyway, all right. So what happens when we used to do area so long ago, and we wanted to approximate area, so we would break this region up into chunks and add some rectangles together and approximate the area, right? Then, to get exact, we took the limit as the width of the rectangles approached 0, and then added the infinite many rectangles together using an integral, right? Okay. We're going to do the same kind of thing with volume by rotation. So what we're going to do, since it's three-dimensional, we can't break into rectangles. Those are 2D. We need a 3D shape. So what we do is we slice it into little cylinders. So these little cylinders, which we call discs, right? So these little cylinders, they have area, pi r squared, but they have a thickness. That's like, we would call that the height if the cylinder was oriented this way, right? So do you guys know volume of a cylinder? Pi r squared h, right? Okay. So the volume of this little disc is pi r. Turn off all. Okay. There we go. Okay. Is pi. I don't need a button. Okay. Is pi r squared h, where h is the thickness of the cylinder, right? So if we take all these discs and add them all together, we get the volume of the whole thing. So the point for getting the exact volume is to take the limit as the height, by height I mean width, of the cylinders approaches 0. And then really what you're doing is you're basically just adding infinitely many circles together. There we go. Infinitely many circles together, starting here and ending here to get your whole volume. All right, so that's what we're doing. So this is just kind of a little visual. So you have some shape. In this case, it's a sphere. You slice it, and you create, you just slice it into a bunch of little cylinders and add the volumes of all the cylinders together. Okay. All right. So I'm not going to make you do that approximate. We're just going to jump right into the calculus. So, and I'm going to skip this. Okay, it doesn't look like an elephant. The elephant is just like a link to what it looks like. All right. So, I know you don't remember because we didn't do that thing it says yet. So that's okay. So the first thing you're going to write down is just the formula for disk method. So disk method says that volume equals pi r squared, and then the dx or the dy, that's your height. That's like the thickness of the cylinders. So it's kind of, when you take delta x, right? So this would be like, this width would be a delta x. If you take the limit as delta x approaches 0, that delta x becomes a dx, right? So, so this is really, the volume is the volume of a cylinder, where the width is approaching 0, and then you're adding all of them together, starting at a and ending at b. So remember, an integral gives you an infinite sum. All right, I gotta fix this poor student. Fix their little shape here. All right. Okay. Okay. So this formula you got to know. So just think pi r squared dx or dy. When you do area, you get to choose. Do I want to do top minus bottom, or do I want to do right minus left? You can pick. Whichever one you like better is fine. Area doesn't really matter as long as you can set up a proper integral for it. You could do dx or dy, whatever floats your boat. In volume, you don't get to pick. So when you're doing volume, you have to use what's appropriate. If you are spinning or revolving about a horizontal axis, you have to integrate with respect to x. So it's a dx problem. If you are revolving about a vertical axis, you have to integrate with respect to y, and it's a dy problem. The only thing you have to find in these problems, besides like your starting and stopping points, is your radius. And that's going to be our main focus today, is finding the right radius for each problem. When you're in dx world, your radius is top minus bottom. When you're in dy world, your radius is right minus left. All right, everyone have all of this down? Another minute. Yes.
So
we're not going to find a volume of a sphere. We're going to find a volume of this thing. Do you have a formula for this? No. Right? Yeah. So really, finding volume is a big deal, especially when it comes to packaging. So before you mass produce, 10 million of these, it's good to know how much they're going to hold, right? So you can, if you identify a function, and it's really not hard to do a quick regression equation that will map out this outline, you can find the volume of what this would be very easily. So I've had students. I have one student in the past whose dad was a packaging engineer. Anyone in here have parents who are packaging engineers? Really?
Yeah.
Do they use calculus? Probably.
I don't know.
Okay. They probably use computer programs to do it. You never know though. But anyway, so finding the right size package for the object, whatever's going into it, is a big deal, right? Because packaging costs money. And especially now that we have everything's getting packaged, right? The whole world's getting shipped. So anyway, packaging engineers, but most of the time packaging engineers tend to work for pre-made products like food or things that come in a package. So anyway, field career opportunity, packaging engineers. But you have to know the volume of your shape. And so what we're learning today is volumes of things that have cross sections that are circles. On Monday, we're going to learn how to find volumes of things that have cross sections that are squares and rectangles and triangles and trapezoids and all that kind of stuff, all these different funky shapes. And then in Calc 3, you get to learn how to find volumes of mountain ranges and stuff, like all kinds of funky things. It's really fun. So anyway. Okay, so we're going to start with this. So find the volume of the solid formed by rotating the graph bounded by y equals 4 minus x squared. We're just going to start with A, so don't worry about B or C or D yet. So find the volume of the solid formed by rotating the graph bounded by y equals 4 minus x squared and y equals 0 about the x-axis. When they say about, that means that whatever's following the word about is your axis of revolution. So we are rotating whatever bounded region we get around the x-axis. When you do these problems, the first thing you're going to want to do is sketch a picture of your region. So, just the bounded region. Don't try to sketch the 3D shape. We don't have to sketch the 3D shapes. We just need to sketch the region that we're revolving. So it's bounded by 4 minus x squared. Y equals x squared is a what? Parabola. Okay, negative x squared turns it upside down, and then plus 4 shifts it up 4. So 4 minus x squared looks something like that. Pretend it's symmetrical. All right, so we've got our 4 minus x squared. Yeah, that's a little better. Y equals 0. Which axis is that? That's the x-axis. So the region that we are revolving has two boundaries. It has the parabola and the x-axis. The region with just those two boundaries is that region right there. Does everyone understand how I found the bounded region between those two functions? Okay. So we are taking this region and we're spinning it about the x-axis, so we're spinning it this way. So if you can visualize the shape, that's awesome. Not everyone can. Being able to visualize shapes in 3 dimensions abstractly is one of there's a maturity marker for it. It's like there are certain abilities that you are able to do as your brain grows and develops. And this one doesn't happen until the teen years. And it can happen anytime between the ages of 13 and 22. So if you might be able to visualize it and you might not. And if you can't, there's nothing wrong with you. It just means your brain hasn't developed up to that point yet. And if you came back like 2 years from now and tried again, you'd probably be able to do it. So it's always interesting, students who can and students who can't. So how many, just curious, how many of you can visualize what the shape looks like? The vast majority. Okay. All right. So anyone want to tell me what it looks like? Give me a filled-in donut. Yes, exactly. It's a jelly-filled, right? Yeah. I like to think of it as like if you took a yoga ball and sat on it, right? Okay. All right. But then you have to turn it sideways. All right. So you have to sit on it sideways. Okay. All right. So anyway, but if you can't visualize, it's okay, right? You don't need the 3D shape to get the problems right. So the next thing you have to find your limits. Bless you. First, we're spinning about the x-axis. Is this going to be a dx or a dy? This is a dx because our axis is horizontal, right? Okay, so this is a dx, which means our limits have to be x values. So it's the leftmost x value to the rightmost x value of your bounded region. Okay, so we have to find those two x values. How are we going to find those two x values? It's where 4 minus x squared equals 0, right? It's the points of intersection of our two boundaries. So you go 4 minus x squared equals 0. So what are the two x values? Why is this? Okay, negative 2 to 2. It's like a shape down there. It's really weird. Okay. Okay, so now we've got that. So now the next thing we need is our radius. This is the most important part of the integral. When you set up your integral, remember volume is pi r squared dx or dy, right? So I always put the pi out front and then just multiply it by the answer at the end. It's up to you if you want to put the pi into the integral or keep it outside. It doesn't matter. So I always put it outside. But don't forget the pi, right? It's like when you go to Thanksgiving, like don't forget the pi, right? Okay, so you have pi times something squared dx, and we already know our limits are negative 2 to 2. So all we have to figure out is what goes in here. Since this is a dx, our radius is going to be top minus bottom. So you go to your shaded region, and you go to whatever function's on top. It doesn't matter where you are, just as long as you're on the upper boundary to the lower boundary, whatever function's on top minus whatever function's on the bottom. The function on top is y equals 4 minus x squared. The function on the bottom is y equals 0. So our radius is 4 minus x squared minus 0. Top minus bottom. So you take your radius and you just stick it in there. The two most common mistakes with these problems, number one is forgetting the pi, and number two is forgetting to square the radius, especially if there's a square in the radius. People forget you still have to square the whole thing, right? So always be saying to yourself, pi r squared, pi r squared. Okay. All right. So what I want you guys to do right now is read part B and just see if you can draw the shaded region for part B. The shaded region for part B, it has y equals 4 minus x squared, but it's also bounded by y equals 5, x equals negative 2, and x equals 2. 4 boundaries for part B. Take a minute in your group, see if you can find that shaded region. We're not going to, by the way, we're not going to evaluate B. All right, so we have 4 minus x squared. Then we have y equals 5, which is up here. Then x equals negative 2, which is that line, and x equals 2, which is that line. So what part has all 4 of these boundaries? That guy. That guy has all four. So do you know what it's like, what I think of with these shapes when you have this kind of a thing going on? I think of it as like the wheel that the tire goes into, right? It's like this. It's got this. It's revolving about this line, so it's going up like that. It's not going down. There's no space inside. It's solid. It's revolving this way, right? Yeah, sorry.
So is it going like that, or is it going like if this is the y equals 5?
Yeah.
Is it just going up like that, or
Exactly.
is it going up and around?
Well, it's going all the way around.
Oh, okay.
Yeah, it's going
I
all
thought
the way
it was just
around.
going up and down.
No. I can't physically go through the board, right? When I'm demonstrating. But like if
And then it's like your line, right? It's in or out. Keep you wrap around, you still.
if this is the axis and this is the shape, it's going all the way around.
Oh, okay.
Yeah, going all the way around. Okay? They all of these shapes spin all the way around the axis. Yes. Yeah, you can think it's like a spool of or it's like a wire spool. You ever seen those? Yeah. It would be like this. Yes, exactly.
Wait, so it's almost like it's like two like circles on each end, like half.
Oh yeah.
Like a yo-yo. Like a yo-yo spindle.
There are two big circles on each end, but there are circles all the way through. They just get smaller as you go in. Yes. So, okay. Now, again, we don't have to visualize it. That's not it is important for life, but for us to do the problems, we don't have to, right? Okay. So the main thing we need to do now, and I'm just going to label again. This is -2. This is 2. Up here, we're at 5, right? Okay. Is the axis horizontal or vertical? Horizontal. So this is still going to be a dx problem, right? So no matter what, our volume is still going to be pi integral -2 to 2 of something squared dx. And you'll see me a lot kind of write a template for the volume and then fill in. Because then I don't forget the pi and I don't forget the squared. So I would kind of write it with an open parenthesis and then I stick the radius in there once I find it. All right, radius. That's where dx, it's top minus bottom. You go to your shaded region, find the top, find the bottom, whatever function's on top, whatever function's on the bottom. For this problem, what function is on top?
Y equals
5. What function is on the bottom? 4 minus x squared. And you can put the radius in unsimplified or simplified. I honestly do not care. Does that make sense? Okay, you just found the volume of a wire spool. All right. Part C. We're going to revolve 4 minus x squared bounded by both axes in the first quadrant about the y-axis. So we have 4 minus x squared. We're bounded by the y-axis and the x-axis, and we only want the first quadrant. So we end up with that guy. One of the things to keep in mind is part A, we gave you 1, 2 boundaries, and your region has 1, 2 boundaries. Part B, we gave you 4 boundaries, so you count 1, 2, 3, 4. Like, make sure you use all the boundaries that are given. For part C, we gave you 3 boundaries. 1, 2, 3. You should use all 3 boundaries, right? Okay. So we're revolving about the y-axis. So this one's going to be a dy because it's a vertical line, right? by the way, don't watch out, because just because it has a y in it doesn't make it a dy. The equation of the y-axis is actually what? X equals 0, right? Okay. All right. So, let's do our radius first, just to mix it up a little bit. So since we're dy, the radius is going to be right minus left. Now, this equation is y equals 4 minus x squared. But since we're dy, we can't put 4 minus x squared into an integral with a dy. You've got to match your variables. So we got to solve this for x in terms of y. So take 10 seconds, solve this for x. All right, so we all figured out x is the square root of 4 minus y. Now, technically, x is plus or minus the square root of 4 minus y. However, since we're only doing the right side, it's just the positive. If we were doing the left side, that would be the negative, right? Because this is where our x's are positive, and this is where our x's are negative. So you'd have positive root 4 minus y, negative root 4 minus y. Notice someone said, well, then if you do right minus left, you'd get 0. And I said, no, because you'd have root 4 minus y minus negative root 4 minus y, which equals 2 root 4 minus y, which makes sense, because exactly twice the distance of 4 minus y. So anyway, but we just need the positive, right? So it's just the positive root because we're on the right-hand side. All right, so radius, right minus left. What's on the right? Root 4 minus y. What's on the left? 0. So our volume is pi integral something squared dy. And we just figured out our radius is just root 4 minus y. Limits. Negative 2 to 2?
No.
0 to 2?
No.
0 to 4? Why 0 to 4? Because we are dy, which means our limits have to be y values. So now you've got to go from your lowest y value to your highest y value. So we're going 0 to 4. You ready to try the last one on your own? It's a big one.
Yes.
Okay. All right. The last one, part D, says, find the volume of the solid formed by rotating the graph bounded by y equals 4 minus x squared, y equals 0, y equals 4, and x equals 4 in the first quadrant about the line x equals 4. So the first thing you got to figure out is how to sketch that bounded region. Draw the region. 4 minus x squared. Y equals 0. That's the x-axis. Y equals 4 is the horizontal line up here. And then x equals 4 is over here. So we end up with that guy. This one tends to make me think of a router bit. Any of you guys use routers? No? Yeah? Do you know what I'm talking about?
Yeah, like the one where you like have the.
Where you slide wood through and it kind of, a router is what takes wood and gives it a nice curved edge, right? You slide it through and it has a bit that spins and takes off the sharp square part and makes it curved, right? So anyway, these make me think of router bits. All right. So anyway, so let's see here. Volume equals pi integral something squared. We're revolving about the line x equals 4. What kind of a line is that? It's a vertical line, which means we are integrating dy. dy. All right, so before we do anything else, what are the limits? 0 to 4, because they have to be y values. So now let's find the radius. Radius is right minus left when you're dy. Right minus left. What function is on the right? X equals 4 minus, what function is on the right? X equals root 4 minus y. How did we do? Yeah, doing okay? Good, because now we have to take it up a notch. For time reasons, I'm going to skip the next example so that we can jump into... Okay, it's time for washer. This is the donut one. Now you'll be able to find the volume of a donut. I know you've always wanted to. Yes. Okay. So volume by washer, a washer is basically just a disc with a hole in the middle. So what a volume by washer method does is it allows you to find the volume of a solid if there's space carved out on the inside. So and all you're really doing is just finding the volume of the solid as though it's solid and then subtracting the volume of the space. So really what washer method is it's just a disk method minus a disk method. It's where this big R, that's the radius of your solid as though the piece was solid. And then this little r, that's the radius of your space that you're subtracting out. And then what you're left with is the volume of what's left. Still dx is your dx if your axis is horizontal, dy if your axis is vertical. Big R and little r, big R is always your outer function. It's the function that's farthest away from the axis of revolution and the axis of revolution. Little r is the function that's nearer to the axis of revolution and the axis of revolution. Now I'm not saying outer function minus axis or axis minus outer function, because it depends. If the axis is above, then it's axis minus function. If the axis is below, it's function minus axis. It's got to be top minus bottom, no matter what. Or right minus left if you're going sideways. So I can't put one minus the other because it could be either way. I really like this shape. It was made by a girl named Megan. Looks like Megan Grover in 2009. This is supposed to be the function y equals sine x revolved about the whatever axis. So it's missing the circle. The rest of the circles fell off this morning. I got to put them back on.
Wait, when did it go like that?
Well, she only is doing it from 0 to pi.
Oh.
Yeah. So.
Did you teach you in 2009?
No. This was, Mr. Thomas is the one whose students did all these figures. So that was back in the days when extra credit was allowed. We don't do extra credit anymore. Okay. All right. So new problem, again, 4 parts, all washers. Find the volume of the solid formed by revolving the graph bounded by y equals x squared plus 1 and y equals 2 about the x-axis. So part A, let's sketch our region. First thing you always do, is sketch your region. So y equals x squared plus 1. Looks like that. It's just parabola shifted up 1. Y equals 2 is a horizontal line. So that's 2. This is y equals x squared plus 1. And those are only 2 boundaries, so we're We're revolving that guy. We are revolving that about the x-axis. So you end up with, you know, if you want to call it a donut, the inside part would be curvy, but it would be like if you took a knife and made the outside of the part like smooth and flat, right? Because you got this flat part that's going around on the outside, and the inside is this curvy part. Well, it's actually not technically half a donut, but it's a donut with the outer part removed. The innards of the donut. So, anyway, kind of like a tire, because tires have a curved inside, so they fit inside of the wheel well, and the outside of them is pretty much flat. The ones on the road, so more like a tire. Anyway, okay, so here's what we're gonna do. I'm gonna go ahead and set up a template for our volume. So volume. When we do washer, so whenever there's space between your region and your axis, that's how you know you're doing washer, right? So if you have your bounded region and your axis is not one of the boundaries, basically, if there's space in between, then you're in washer method world. And so washer method is big R squared minus little r squared. Is this going to be a dx or a dy? Dx, because we're revolving about a horizontal axis. All right, so go ahead and take a minute and see if you can find your limits first. You need the leftmost x value and the rightmost x value. All right, Faith, what'd you get for your limits? -1 to 1. And the way you get those, if you weren't sure, it's the points of intersection, right? So it's where x squared plus 1 equals 2. So you get x squared minus 1 equals 0. Okay. All right, so we're going -1 to 1. All right, now we need big R and little r. Pay attention here. This is from doing this many, many times, and this is by far the best method. Are you ready? Okay. When you need big R, you start by putting your pencil on the axis of revolution. You always start on the axis of revolution and then draw a line to the farther away boundary. That's big R. You start on the axis and go to the farthest away boundary. And then you do top minus bottom. So big R, what function is on top for big R? 2. What function is on the bottom? 0. So big R is just a constant of 2. Which makes sense, because if we just rotated this line about the axis, we would actually just end up with a cylinder. All right, little r. So little r, you start at the axis and you draw a line to the closer boundary. That's little r. Let's see. What function is on top for little r? X squared plus 1 minus what function is on the bottom? 0. Big R and little r will both always have the axis in them. Always. The axis will be one of the two things for both big R and little r. So big R, you have big R squared minus little r squared. Remember, it's pi big R squared minus little r squared. It's not big R minus little r squared. It's a disk method, minus a separate disk method. Okay, yes?
Do you have to subtract the axis from the big R and little r? So if it was like around y equals 1, it would be 1 squared and x squared?
Yes.
Okay.
Yes.
So you have to subtract.
Yep. And the next one we're going to do is going to have an axis that's not 0. And then you'll see it more clearly. All right. We're going to spin the exact same region, but now we're going to spin it about y equals 5. So we are, for part B, everything's the same, except now we're spinning it about an axis up there. So the limits are still the same, right? You still have pi integral -1 to 1 of something squared minus something squared dx. Everything is the same, but now you have a new big R and little r. I want you guys in your groups to see if you can find big R and little r. Remember, start at the axis, put your pencil on the axis, and go to the farther away function. That's big R. Always start with your pencil on the axis. Axis of revolution.
Can you just go back up to the question? Okay, thank you.
Uh-huh. Yeah. Yes. See, and you thought we were just doing spheres today. Okay. All right, big R, you start on the axis, go to the farther away function. So for big R, what's on top? 5 minus, and then what's on the bottom? X squared plus 1. Which you can keep unsimplified, or if you want to combine like terms and write it as 4 minus x squared, that's fine. All right, little r. Start on the axis, go to the nearer boundary. So what's on top for little r? 5 minus, what's that? 2. So little r is just 3. That makes sense? All right. To save time, I'm just going to jump to D. We're going to do one about a vertical axis, and then we're going to move on. So find the volume revolving y equals x squared plus 1 and x equals 0 and x equals 2. Let me read this again. Y equals x squared plus 1, x equals 0, and y equals 2 in the first quadrant about the line x equals 4. All right, x squared plus 1, x equals 0, and y equals 2 about the line x equals 4. I want you to see if you can sketch the region and find big R and little r. You're going sideways. You're going sideways. I'm going to pause. I'm going to give you a few minutes to stew on this one. All right. So we have x squared plus 1, x equals 0, y equals 2 in the first quadrant about the line x equals 4. All right, so how do I say this? First, is it a dx or a dy? It's a dy. So our volume is going to be pi integral something squared minus something squared dy. All right, the limits. The limits have to be what kind of values? Y values. So you need the lowest y value to the highest y value. What are we going from and to? What are the limits? 1 to 2. Did everyone find the limits 1 to 2? Is that okay? We're all comfortable with that? Okay. All right, now let's find big R and little r. So big R, you start on your axis and you draw to the farthest away boundary, and that's big R. So big R is going to be, well, what's on the right?
4.
What's on the left? 0. So big R is just the constant 4. Little r, you start on the axis, you go to the nearer boundary. What's on the right? 4. Uh-oh. Oh, okay. Let's just see if you got it. What's on the left? Square root of y minus 1. Very good. Did everyone get root y minus 1? And not x squared plus 1? So if this is y equals x squared plus 1, then x equals plus or minus root y minus 1, but we're first quadrant, so it's just the positive. Good. Any questions on that? Fantastic. All right, then we have time for you guys to try a harder one. Yeah, you know what? Let's try this one. Yeah, I like this one because it doesn't have anything flat. So I think you'll like this one. So you don't get out your calculators. We don't have time. All I want are the setups. So see if you can sketch the region, and then see if you can do a setup. Ooh. I meant to do that. Okay. So x, x equals 0, 4. So we have a shape that looks like that. Y equals x is a line that looks like that. Something like that. Not drawn to scale. So I'm going to find the limits first. So I want to know where. Someday. Okay. 4x plus x squared equals x, right? So x squared plus 3x equals 0. So x equals 0 and negative 3. So we know no matter what that we are going from negative 3 to 0 for both of these, right? Okay, so for part A, we're revolving about the line y equals 0, which is the x-axis. Start on the axis, go to the farther function. What's on top? 0. What's on the bottom? 4x plus x squared. So I'm going to write that down. 0 minus 4x plus x. Okay. Little r, start at your axis, go to the nearer function. So little r, what's on top?
0.
0. What's on the bottom? X. I'll put the 0 in just for fun. I love these problems. For me, this test, the one that you're going to take next, I find it the easiest test for me because it's all just formulas and plugging stuff in. There's not a lot of interpreting. It's just do it, right? So it's the whole test is pretty much plug and chug, but you got to learn all of it. Okay. Y equals negative 5. Exact same picture, except now we're revolving. We're revolving about this line down here. So if you draw, let's do B. I'm just going to set it up first. Pi, don't forget pi. So something squared minus something squared dx. Okay, so big R. So for part B, I'm just going to draw right on the same picture. You start at your axis, you go up to, whoops, that's not the farthest away boundary. Erase. Start the axis, go to the farther away boundary. There's big R. Let's pretend that looks good. All right, so big R, what function's on top? X. What function's on the bottom? -5. So it'd be x minus -5 or x plus 5. Little r, start at the axis, go to your nearer boundary. What's on top? 4x plus x squared minus what's on the bottom? -5. All right. All right, that is it. Remember, guys, if there's any space between your shaded region and your axis, any space, it's a washer method, automatically. All right.